So in the last two videos, I talked about the product rule, which is one basic principle of combinatorics. And in this video, I want to talk about another basic principle called the sum rule, which is about when we get to add choices instead of multiplying them. So let me state what it is. So we're trying to choose something, and in this case, choosing something means either making one choice in C1 ways, or making another choice in C2 ways, right? And the choices don't overlap at all. And then the total number of choices is C1 plus C2. Okay, so this is really saying, I've got some set of choices C1, and I've got some other set of choices C2, and they don't overlap at all. How many things are in both? Obviously, it's just the number in here plus the number in there. One example would be, right, so on the activity in class, we did an example where there were two restaurants, and there were you wanted to order one item either from one restaurant or from the other. Now, in the example, the restaurants had some overlapping items, but if we suppose that so there's some restaurants that don't have any overlapping items, then obviously you just add the number of things you could order from one restaurant plus the number of things you could order from the second restaurant. That gives you the total number, right? Now, as in that activity, when they do overlap, right, then we can't use this directly, and we'll talk about that in a subsequent video. But that's a very simple example. So as the main example of this, though, I want to do a sort of more extended example and continue talking about counting binary trees that I did in a previous video. So if we already kind of did this, we talked about how to count binary trees just in an intuitive sense, but if we back up and think about what combinatorial principles we're using. So a binary tree, right, it could either be empty or it could be, right, it can have this kind of branch with its T1 and a T2. And so I could look at this and say, okay, well, choosing a tree that has a branch node is really, I'm making two choices, right? I'm choosing what tree to put over here, and I'm choosing what tree to put over here. The problem is that if we're trying to count the number of trees with a certain number of branch nodes, right, then these two choices are not independent. Because what tree I choose over here, how many branch nodes I choose to put over here, affects what tree I get to pick over here, right? So I have to pick two whose the number of branch nodes adds up to, a certain number, so they're not independent. So we can't directly use the product rule, okay? And this is where the sum rule often comes in. We've got some set that we don't directly know how to count it as a whole. We can't use the product rule. We don't know some other way of counting it. If we can find a clever way of splitting it up, right, and say, well, I have this big set, but I really want to split it up into these sub-pieces, and then each of those pieces are somehow more manageable, right? Then I can use the sum rule and just say, well, I can now add these up. Okay, and that's exactly what we're doing here. So these choices are not independent, right? So we're going to split up the set into manageable pieces. All right, and in particular, the way that we decided to do that was we say, okay, well, let me just count. If I know, say that I want, a total of four branch nodes in the whole thing, I need to have one here, and so then I need to put 3 down here, and we can split it up into cases depending on, do I put 3 nodes over here and 0 over here, or 2 over here and 1 over here, and so on. And in each of those scenarios, these choices are independent, right? If I say, okay, I want to choose a tree over here with 2 nodes and a tree over here with 1 node, right? Those are now independent because I've specified exactly how many nodes I'm picking, so I don't have to worry about that. But I can choose any tree I want with 2 nodes over here, and then any tree I want with 1 node over here, right? Or if I were doing, 15 and 29, those are independent. I can choose a tree with 15 nodes here, any tree with 29 nodes over there. So we split it into non-overlapping sets based on how many nodes go to the left and right. And it's also important to note that, the way we did that, we split it into non-overlapping sets. And that's pretty easy to see because if I have, any tree with 3 nodes over here and a tree with 0 nodes over here, that's definitely going to be different than something where I have 2 nodes over here and 1 node over here. No matter how I choose those, fundamentally anything with 3 nodes here and 0 here is going to be a different tree than having 2 nodes over here and 1 node over here. So those sets don't overlap at all, and so we can split them up that way. So, right, and so obviously this involves the product rule as well. Now that I've, if I have, once I can independently choose these 2 trees, I can multiply how many ways I have of choosing them to tell me how many are in for that particular configuration. And we saw this in that other video I made. So now that we kind of understand this more generally, let's see if we can compute the number for 5. So we had, let me put it up here actually. So we had, we'll say t, so 0 is 1, t sub 1 is 1, so this is the number of trees with a certain number of branch nodes. So there's 1 tree with 0 branches, right, which is just this one. There's 1 tree with a single branch, which is this one. There's 2 with 2 branches, which are these 2, right, and then we had figured out t3 is 5. And I think in a video I made, I showed that T4 was 14, so what about T5? Well, right, again, I'm going to say, well, in that case, I'll have 1 node at the top, and then I have 4 to distribute, and we can split it into cases depending on how many we put on the left and how many we put on the right. And then we can, by the sum rule, we can add those all up. And by the product rule, for each one of those cases, I can just multiply the numbers of choices I have for each tree on each side. So, right, I could either put 4 nodes on the left and 0 on the right, in which case I want to multiply the number of choices for a tree with 4 nodes and a tree with 0 nodes, right? Or I could put 3 on the left and 1 on the right, or 2 on the left and 2 on the right. Okay, those are all the choices. And so now I can just do this. So this is 14 times 1. This is 5 times 1, which is 5. T2 times T2 is 2 squared, which is 4. And this is going to be 5 again and 14. So I get, let's see. Well, this 5 gives me 10. 14 plus 14 is 28, so 38 plus another 4 is 42. And using this scheme, right, I think you can see how to do T6. So I challenge you to see if you can actually figure out the next few values, like for 6, 7, 8. once you see this kind of pattern and how the sum and product, how we're using the sum and product rules together to add these up, it's not too hard to compute the next few numbers, even though it would be really tedious and impossible to actually draw all the trees out by hand. You would definitely miss some.